Hello and welcome to this review introducing electrochemistry. What we'll focus on during this clip is the construction of a half cell and how we measure and calculate standard electrode potentials. We'll also pay a little bit of attention to predicting direction of reaction using electrochemical data. So a half cell is the representation of oxidation or reduction in an electrochemical system. So all electrochemical systems are redox reactions where each of the two parts of the redox system occur in different places, and the two locations are connected by electrical wires. It can be in two beakers, it could be in two parts of a battery, but basically the reactants are in separate places and they're connected by electrical wires to allow the electrons to flow. So if the two half cells are connected, electrons can flow between them and therefore the redox reaction can take place. So if we were to take our half cell that we had a second ago and connect it up to another half cell, one of the half cells will take the negative role and one will take a positive role. So how is this determined? So this is worked out by using the electrode potential, which is written as a capital E with a superscript standard sign. And it's measured in volts, and it is a separate value for each half cell. So this information comes from what we call the electrochemical series, which is loosely related to the reactivity series you would have learned at GCSE and before. What would happen in an exam, for example, you'd be given the relevant ones for your question, so you don't have to worry about remembering any of them. The important thing to know what to do is to use them correctly. So you'll probably have noticed by now that both of the half equations have been written as reductions. You obviously can't have a redox system from two reductions, so one of them is going to have to become an oxidation. The reason I did this is because the convention is normally to write out half equations individually as reductions. If you look at an electrochemical series in a textbook or online, you'll see that they're all written out as reductions. So I've taken a downloaded example, and you can see that they're all written out as reductions. This is what you'd be provided with in a question, and you'd have to then do some maths with it. So, how do you decide which is the positive and which is the negative half cell? So you look at both of the electrode potential values and then decide which one is more positive. So in this pair, you can see that the copper is more positive. So you can see that the zinc half cell is reversed. So if it's reversed, it becomes an oxidation. So that means it's losing electrons. So if it's losing electrons in that direction, the direction of the arrow, that must mean that the electrons are building up. So if the electrons build up, that particular half cell must become negatively charged. So now we can assign polarity to the two halves of our overall electrochemical system. On the copper side, you're gaining electrons. On the zinc side, you're losing electrons. So this poses a bit of a problem now. So if we take the black arrows to represent the direction of electron flow, the circuit still isn't complete. So if this is allowed to continue, eventually the electrons will build up on the left-hand side. They'll simply transfer from the zinc side to the copper side. And therefore that means the copper half cell will no longer be positive because it's having a build-up of negative charge. So the flow of electrons and the reaction, therefore, will stop. So the salt bridge connects the two half cells in the middle, and it contains a saturated solution of anions, in other words negative ions, specifically or mostly nitrate in vast majority of cases, because nitrate's extremely soluble in water. And what this does is it carries the negative charge back across, as indicated by the white arrow. And now this completes the circuit, so the reaction can be maintained. So to summarise what's going on so far, electrons will flow from from where there are a lot of them, in other words a negatively charged region, to where there's less of them, a positively charged region. And the wires connecting the two terminals allow this to happen between the half cells. The salt bridge consists of a saturated solution of anions which completes the circuit and prevents the build-up of negative charge in the positive half cell. Simultaneously, the salt bridge allows positive ions formed in the negative half cell on the right-hand side to escape across to the positive half cell in the other direction, and this prevents the positive charges building up in the negative half cell. So in other words, the reaction is maintained and the charges on each side are maintained. So if you want to calculate the cell potential, which is the overall voltage in the cell, what you need to do is subtract the more negative electrode potential from the more positive electrode potential. So just a reminder that the cell potential is the overall electromotive force of the whole cell, and it's what you'd see on the high resistance voltmeter. So for this particular system, you'd take plus 0.34 minus 0.76, and the overall cell potential would be plus 1.1 volts. So because both half cells are essentially equilibria, which you can see that I've now changed them into, as equilibria, they're sensitive to variations in temperature and they're sensitive to changes in concentration. So cell potential can actually be affected by non-standard conditions. That's why we have to put a little standard sign next to the capital E. So let's now take a quick look at how we actually get the electrode potentials in the first place. How are they measured? How are they arrived at? So we use the standard hydrogen electrode and we connect this up to another cell that we're trying to measure the electrode potential for. So in this standard hydrogen electrode, there's a very specific set of conditions. You must have the hydrogen at 298 K in 1 atmosphere. You must have a platinum electrode because it's inert. And you must have an acid solution containing hydrogen ions at 1 mole per decimeter to the minus 3. So to achieve this, the acid can either be 1 molar HCl or 0.5 molar H2SO4. And as you can see from the diagram I've added to the bottom of the screen, both solutions must be equimolar once it's connected to the half cell you're measuring. So the half cell in the standard hydrogen electrode is 2H plus in aqueous solution, giving you H2 gas plus 2 electrons, and the electrode potential for that half reaction is 0.00 volts. So therefore, this is called a reference electrode. So obviously, the voltmeter will display the electrode potential of the other half cell. In doing this, the standard hydrogen electrode can be used as a reference cell. So to finish off, let's have a look at some other types of cell. So when you get a reaction where two ions are actually reacting with each other, you have to use a special type of cell here. So the platinum electrode must be used because as a metal it's too unreactive to interfere with the half reaction that's above in red. Standard conditions are maintained by making sure that both the ions are in the same concentration, and if we're measuring this using a standard hydrogen electrode, all we'd have to do is connect it up with a voltmeter and we'd get the electrode potential of this particular half cell. So I mentioned at the beginning that I'd talk briefly about predicting the direction of reaction. I'm not going to go into it in massive detail, I'm just going to make a passing reference to it because it's going to be covered in a separate clip. So let's say you're given a set of electrochemical data like this. First thing you do is you look at the pair of species you're being asked to consider. Then, using their electrode potential values, decide which one is more positive, and this will be the reduction, and the other half equation will be reversed. And if you're given two species where the electrode potential data suggests that the reaction will not proceed in a certain direction, then this is said to be unfeasible. So if you take chromium 3+, it won't react with copper 2+, because its half-cell electrode potential is more negative, so it'll actually go back in the other direction. It'll be reversed. So chromium metal will react with copper 2+, but chromium 3+ will not react with copper 2+. So although I've just introduced maybe a slightly more challenging idea in terms of reaction prediction, I will cover this in a separate clip, but I did say at the beginning that I'd make some mention of it, so that's what I've just done. It might be worth going and having a look at some typical examples and maybe even choosing some pairings from this table and seeing if you can work out what direction the reaction will go in. So I'll leave that with you as a little exercise to practice this idea. But in the meantime, thanks for listening and see you soon.